The geometric interpretation of a zero. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on the algebraic definition of the zeros of a polynomial. Specifically, we learned that if we are working with a polynomial, which we denote as p of x, a real number, let's call it k, is considered a zero of that polynomial if, when we substitute k into the equation, p of k equals 0. Up until now, we have been working purely with numbers and equations. However, today, we are going to shift our perspective. We are going to explore how this algebraic concept, this idea of finding where an equation equals 0, is actually represented visually on a coordinate plane. We're moving from the world of algebra into the world of geometry. Understanding the coordinate plane connection. To truly understand the geometric meaning of these zeros, we first need to represent our polynomial, p of x, as a function of x. We achieve this simply by setting y equal to p of x. When we take this equation and plot it on a Cartesian plane, we are working with two perpendicular lines: the horizontal axis, which we call the x-axis, and the vertical axis, which we call the y-axis. Every single point you see on this graph is represented by a pair of coordinates, x and y. However, because we have specifically defined y as being equal to p of x, we can be more precise. Every point on this graph can be written using the coordinates x and p of x. Now that we've recalled the algebraic definition of a zero from our previous discussion, let's move into the second slide to bridge the gap between algebra and geometry. This setup is crucial because, as we will see in the next slide, it allows us to identify exactly what happens when that y value reaches 0. The significance of the x-dollar axis. The x-axis is a very special line in geometry. Think about it. If you are looking at any point that lies exactly on the x-axis, there is no upward or downward movement away from the horizontal line. This means the vertical distance from the origin is exactly 0. Because there is no vertical displacement, we can conclude that for every single point located on the x-axis, the y-coordinate is always 0. So, if we were to write this out mathematically, any point sitting on the x-axis will always take the form of x, 0. Keep this specific coordinate structure in mind, because in the next slide, we are going to use this fact to bridge the gap between our algebraic equations and our visual graphs. Now that we've established how to represent our polynomial as a function on a coordinate plane, let's focus on one very specific part of that plane. Connecting algebra to geometry. Now that we have looked at the algebraic definition and the properties of the x-axis separately, let us bring these two ideas together to see the big picture. Think back to our first few slides. Algebraically, we defined a zero as a specific value, let's call it k, such that p of k equals 0. On the other hand, as we just discussed in the previous slide, any point sitting directly on the x-axis must have a y-coordinate of 0. So here is the magic moment where algebra meets geometry. If we take our function, where y equals p of x, and we substitute it into our condition for the x-axis, which is that y must equal 0, we are left with the equation, p of x equals 0. What does this tell us? It tells us that the values of x where the graph of y equals p of x actually hits, or even just touches the x-axis, are exactly the same values we call the zeros of the polynomial. In short, the algebra and the graph are telling us the exact same story. This connection is what we will use to solve more complex problems, like the example coming up in the next few slides. Real-world analogy, the diver. Now, sometimes abstract math can feel a bit disconnected from reality, so let's use a real-world analogy to make this concept more concrete. Imagine a diver jumping from a high diving board into a swimming pool. To connect this to our graph, let's let the surface of the water represent the x-axis. Now, we can use a polynomial to track the diver's movement. Let's say the height of the diver above the water at any given time, which we'll call t, is represented by the polynomial p of t. Think about the position of the diver in relation to that water surface. While the diver is still in the air, their height is greater than 0, which we write as p of t is greater than 0. On our coordinate plane, this means the graph is sitting above the x-axis. However, the very moment the diver hits the water, their height becomes exactly 0. So, if we look at this geometrically, the specific point where the diver's path intersects the water surface is exactly what we call the 0 of our height polynomial. This perfectly illustrates how the algebraic 0 and the geometric intersection are one and the same. Now, let's look at a quick step-by-step example to see this in action with actual numbers. Step-by-step example. Now that we have understood the theory behind how algebra and geometry connect, let's put it into practice with a concrete, step-by-step example. Let's take a very simple linear polynomial, which we can call p of x, where p of x equals x minus 2. First, let's go back to our algebraic roots in step 1 and find the 0 using algebra. To do this, we simply set the entire polynomial equal to 0. So, we write x minus 2 equals 0. By adding 2 to both sides, we find that x equals 2. Therefore, algebraically, our 0 is 2. In step 2, we move toward the geometric side by representing this polynomial as a function. We do this by setting y equal to our polynomial, so we write y equals x minus 2. This allows us to prepare for plotting it on the Cartesian plane, just like we discussed in the previous slides. Now in step 3, we need to identify some specific points so we can actually draw the graph. Let's pick two values for x first. If we let x be 0, then y becomes 0 minus 2, which is negative 2. This gives us our first coordinate point, 0, negative 2. Next, let's use the 0 we found earlier. If we let x be 2, then y becomes 2 minus 2, which is 0. This gives us our second point, 2, 0. Finally, in step 4, let's observe the graph. If you were to plot these 2 points on a coordinate plane and draw a straight line through them, you would see something very important. You'll notice that the line crosses the x-axis exactly at the point 2, 0. Look closely at that intersection. The x-coordinate of this point is 2, which is exactly the same 0 we calculated algebraically in our first step. This perfectly demonstrates the connection we've been building toward, and as we will see in our final summary, this pattern holds true for much more complex polynomials as well. Key takeaways. First, let's revisit our main definition. We have seen that the zeros of a polynomial, which we call p of x, are simply the x-coordinates of the specific points where the graph of y equals p of x meets the x-axis. This could mean the graph actually crosses through the axis, or it might just graze or touch the axis and then turn away. Either way, that x value is a 0. Now, why does this happen? It's because of the logic we established earlier. At any point where the graph intersects the x-axis, the vertical distance from the origin is 0, meaning the y value is exactly 0. This perfectly satisfies our algebraic condition where p of k equals 0. So, to put it in one simple, professional term, geometrically speaking, finding the zeros of a polynomial is exactly the same thing as finding the x-intercepts of its graph. All right, let's bring everything we've discussed today together into a clear summary. Now, before we wrap up, I want to point out a couple of common pitfalls to watch out for in your upcoming assignments. Common mistakes. First, let's talk about the confusion between x-intercepts and y-intercepts. It is very common to see a graph and mistakenly identify the point where the curve crosses the vertical y-axis as the 0. However, remember our core definition from earlier. A 0 occurs specifically when the value of the polynomial, which we represent as y, is equal to 0. As we discussed in slide 3, the only points where the y-coordinate is 0 are the points sitting directly on the horizontal x-axis. So, always remind yourself, the 0 is found where the graph meets the x-axis, not the y-axis. Second, please be careful not to ignore touching points. When we look at a graph, we often expect the line to pass straight through the x-axis, like the diver hitting the water in our analogy. But a polynomial doesn't always have to cross from one side to the other. Sometimes, the graph might descend, just graze or touch the x-axis, and then immediately turn back upward. Even in this case, because the y value at that exact moment is 0, that point is still officially a 0 of the polynomial. Don't let a bounce off the axis trick you into thinking there isn't a solution there. Now, before we conclude our lesson, I want to highlight two common pitfalls that students frequently encounter when working with the geometric interpretation of zeros. It is vital to address these now so you can avoid them in your future calculations. Keep these 2 points in mind, and you will have a much more accurate way of interpreting these graphs.